Episode 2, Episode 2, Episode 2, Episode 2, with better mic quality. I don't know. I wrote the script before about the mic, so maybe not. But let's cut all the intro stuff and just get straight into the meat of the episode, right, don't we? What are we covering today? Well, you saw the thumbnail. What is it? C, Team Fortress 2. Now, I love TF2. It's one of only 2 online shooter games I enjoy playing, the other being Splatoon, of course. This is actually the first part of a 3-part sub-series I'm planning on, which I am dubbing the Valve Holy Trinity. The Valve Holy Trinity includes Team Fortress 2, Portal, and, of course, Half-Life, which I just started playing. Holy good games. I like it. Now, one of the most iconic parts of TF2 is its rocket jump. Rocket jumping is in a plethora of other games, but nothing has perfected it like TF2 has. But what about real life? Well, Vsauce 3 actually has an answer for us. No? You can't? It would kill you? But what if somehow it didn't? What if all of the energy inside of the rocket was converted entirely into kinetic energy absorbed by your body? How far and fast would you go? Not even in TF2 is this the case. Clearly, in the game, a decent part of the energy is converted to a fireball and damaging the player. So just how efficient are the TF2 rocket launchers? That's what I'm here to answer. This is Scidia, where we discuss the fictional science of very fictional media. Now let's break down the question. To find how efficient TF2 rocket launchers are, we're going to have to collect a plethora of data. It's the second time I've used that word this video. How powerful is the rocket launcher? How fast would you travel? How long would you travel? And how far would you travel? That's so much data, I could make an Excel sheet out of it. So how exactly do we find how powerful a fictional rocket launcher is? Well, since we're basing this episode off TF2, I figured I would use a period-accurate weapon. Team Fortress 2 takes place in 1968. The United States was currently engaged in the Vietnam War, so I decided to use the most common rocket launcher during the war. In my research, I found 2 possible rockets: the M72 Law and the M202 Flash. I ended up settling on the latter for a couple of reasons, but mainly because it was the first one I saw. So our next question is, how much energy is released from the M202 Flash? The main component in the M202 Flash is triethyl aluminum. It is highly flammable in air and especially in water where it is aggressively oxidized. The M202 Flash was actually developed to replace the flamethrowers of World War II. However, don't get it wrong, this puppy still packs one hell of a punch.
The M202 66mm rocket launcher with M74 incendiary rockets is planned as a replacement for the standard portable flamethrower. Capable of firing 4 incendiary rockets in 4 seconds, the weapon can be used to attack bunkers, automatic weapon positions, and materiel. Its 200-yard range for point targets is more than triple that of the flamethrower, and it can be used against area targets up to 700 yards away.
So, how much energy is released? Well, we're going to have to do some math. According to the Wikipedia page, triethyl aluminum, the active ingredient in the N2O2 flash, has a delta H, change in enthalpy or energy, of negative 5,105.7 kilojoules per mole. This means that for every mole, 6.022 times 10 to the 27th particles of triethyl aluminum combusted, 5,105.7 kilojoules are released. The warheads for the N2O2 flash contain about 610 grams of triethyl aluminum. In order to convert this to moles, we're going to need to use the molar mass. The molar mass of triethyl aluminum is 228.355 grams per mole. We divide our 610 grams by this 228.355 grams per mole. The grams will cancel, and we will get the moles of triethyl aluminum and an N2O2 warhead. We find that we have 2.67 moles of triethyl aluminum. Multiplying by the previous 5,105.7 kilojoules per mole and converting kilojoules to joules, we get a grand total of 13,631,952 joules. That's a lot of energy. That's about 0.32% of a metric ton of TNT. Again, massive percent of this energy would be given off as a fireball. If I had to wager a guess, probably about 90% or so. And most of it wouldn't even be given off instantly. It would go off pretty quick, but still in decent increments. The rest of the 10% is a mix of the shockwave, shrapnel, light, and of course, the direct upward kinetic energy absorbed by us. So now that we have our data, it is pure plug and chug from here. Yeehaw! To find the velocity, we're going to be using the equation kinetic energy equals 1/2 the mass times the velocity squared. We can rearrange this equation to solve for velocity to give us velocity equals the square root of 2 times the kinetic energy divided by the mass. We now just plug in our numbers. I'm going to use the weight of the average American plus the weight of the loaded rocket launcher being 92.77 kilograms, give or take some depending on the person's weight and the weight of the rocket launcher after firing. The kinetic energy will be our 13,631,952 that we found earlier. Again, we're assuming all of this energy is converted into kinetic energy. After plugging this into the calculator, we get a velocity of 542.11 meters per second, which is equivalent to 1,951.6 kilometers per hour, or 1,212.67 miles per hour. That's equivalent to 158% the speed of sound, or about double the top speed of a Boeing 737. However, since this is given instantaneously and there is no continuous acceleration, the speed will soon be countered by gravity, which segues us into our next topic. In order to find our answer, we're going to use one of my favorite branches of physics and mechanics, kinematics. Kinematics is all about tracking the motion of an object in its simplest form, which we have brought the problem down to. There are a bajillion for kinematic equations, but we're only going to need 2. Velocity final equals velocity initial plus acceleration times time. And our other equation, delta y equals velocity initial times time plus 1/2 acceleration times time squared. Times time. If you're not an autistic physics major like me, you're probably a little confused. Why are there 2 velocities? We don't have a number for acceleration. What the fuck is a delta y? Well, don't worry. I assure you, we already have all the data we need. I'll walk you guys through these equations, variable by variable. Starting with the equation for final velocity. what even is the difference between final and initial velocity, and which one is our 542.11 meters per second? Initial velocity is the velocity at t equals 0, time equals 0 seconds, when we first start tracking our projectile. This will be our 542.11 meters per second. So what is velocity final? Since our projectile is going up and then falling back down to the ground in a parabola, we know that when it reaches the peak of the parabola, its upward velocity will be 0, and then quickly gain velocity back down until hitting the ground at 0. Next up is acceleration. Since the force applied to the explosion was instantaneous, there is no upward acceleration. However, there is downward acceleration. Specifically, the acceleration caused by the gravitational force of the Earth. The acceleration of the Earth is constant at 9.81 meters per second squared. Since this is pulling our projectile down, it will be negative. The final variable, time, is actually what we will be solving for in this equation. We rearrange the formula so time is the only variable on the side of the formula, and we get t equals velocity final minus velocity initial, all divided by a. We plug in all of our numbers and we find that it takes 55.26 seconds to reach the peak of our trajectory. And now we can work with our second equation, delta y equals velocity initial times time plus half acceleration times time squared. Starting on the left, what we're solving for, delta y is displacement. Essentially, how far away is the projectile's final position from its initial position? This will be our height. The most important variable on the right side of the equation is t, time. To find the max height traveled, we need to know what time it reached that height, which we just found, 55.26 seconds. Is the time it took to reach velocity final equals 0, or when it was at the top of the trajectory. This is also when delta y is at its max. With this being said, we already have all the numbers and don't even need to rearrange the equation. We plug in the data and get a total height of 14,972.68 meters, which is roughly 15 kilometers or about 9.3 miles. That's right about the edge of space. Yeah, I wasn't kidding when I said there was a lot of math in this video. And we're not even done yet. We haven't even gotten to the Excel sheet. The Excel sheet is where the real magic happens. As I've said a million times now, we're assuming that 100% of the energy is converted into uniform upward velocity. And as I've said a million more times, this is extremely wrong. To account for this, I made this table in the Excel sheet. You may have noticed that the top row are all numbers we used before. That's because we are at 100% energy efficiency. As you go down the table, you notice the numbers get smaller according to the percent in the leftmost column. The leftmost column represents the efficiency. What percent of energy is converted to uniform upward velocity? Each row decreasing until we reach 0.001%, where you would barely be lifted off the ground. The columns all represent important numbers: speed, meters per second, time, seconds, and height, meters. I then created a graph showing the relationship between percent efficiency and height traveled, which gave us this beautiful linear trend line. The equation for this line lets us convert the displacement, or max height, to percent efficiency, which will be very important in just a second. For the fun of it, I also created a graph relating velocity and percent efficiency and got this beautiful curve here. Did you forget this was about a video game? I did. God, the viewer retention is going to be awful on this one. Congrats for making it this far, though. You're a real nerd. And you know what a real nerd would do? Like and subscribe. So to answer our third question, just how efficient are the TF2 rocket launchers? We're actually going to use experimental data and the second table. I made in the Excel sheet. This time, the table has 16 rows labeled trial 1 through 15 and mean. There are also 4 columns labeled height in feet, height in meters, efficiency in percent, and energy in joules. We will be inputting our experimental data in the column height feet. The Excel sheet will then do the rest of the conversions and calculations for us. After we input all 15 heights, we will automatically get a nice average capping off the question and this video. If you want to know how I got all these numbers automatically, watch a fucking Excel tutorial. Now let's get to the actual experiment. I had TF2 pulled up on my desktop and my laptop on the left with the Excel sheet. After over an hour of reading 8-year-old Steam forums and abandoned and locked TF2 forums, and eventually getting an answer from a YouTube video description, I got my buddy Gingy from JJJReact. Check out his channel if you want to see our shitty middle school YouTube videos. I got him into a private server to record my trials. Please, Valve, update your game. Please. After some searching through some maps, we settled on this spot here in Nucleus. I set Gingy in this spot right here and made sure he didn't move an inch after we started, to avoid any parallax scaling issues. I would aim myself right at the end of this wall and edge and did 15 rocket jumps. Gingy recorded each one individually, the footage you're watching right now in fact. He sent them to me and I then, very scientifically, taped a piece of 8.5 by 11 printer paper to my computer screen. I labeled it by intervals of soldier lengths. That's because soldier is canonically 6 foot tall, so if I traveled 4 soldier lengths, I know I traveled 24 feet. From my 15 trials, the highest I traveled was 48 feet, or 14.64 meters. The lowest I traveled was 42 feet, or 12.82 meters. Now watch me utterly destroy Gingy. All trials considered, I came out with a mean height of 13.5 meters, with a standard deviation of 0.609 meters. Oh yeah, I added a standard deviation while writing the script, for the fun of it. Using the equation we found from our graph, we can convert the average of the 15 to find the efficiency of a TF2 rocket jump. Using the answer, we get an answer of 0.09% efficient. This means 0.09% of 13 megajoules or 12 kilojoules, 12,000 joules of energy is absorbed in a TF2 rocket jump. I was really happy with the number we came up with. It really does seem somewhat realistic to me. This is kind of a hard thing to gauge, of course, especially since the rocket we're using is primarily incendiary. If we were to use another rocket with similar energy but didn't spend as much of that on fire and instead the shockwave, I would expect to see a similar number in real life. This is all conjecture, of course, because rocket jumping is very impossible and very dangerous. Surprise, surprise. But this is exactly the kind of thing I enjoy talking about, and what this channel is for. If you love this kind of thing, of course, like, subscribe, check out the last video, all that. But if you want to work on this problem more, I've actually left a link to download my Excel file in the description. If you want to do your own 15 trials to test your own efficiency, use the Excel sheet. If you want to research a different explosive, do a different rocket launcher, see how far what percent efficiency that would be, use the Excel sheet. There will be 2 files in the description, one filled with the data I used in the video, and one blank. Criticize my methods as much as possible. That's what I'm here for. Next to the Excel sheets, you'll also see a link for a Google form. This form has the purpose of helping me improve the channel. If you have a piece of media you want to see an episode on, or a question you want answered, put it in the form. If you want to have your voice heard and help out the channel, please fill out the form. Hopefully, see you guys next time for the second part of the Valve Holy Trinity Portal.